path that we defined. The only limitation was that we were not allowed to have any sensors on the rover itself. We used an external sensor network to help get us position data to help drive and steer the rover. Requirements were to help the rover navigate across a set of points. It has to be completely autonomous. The system has to be robust. The system is broken up into 3 separate components: sensor, controller, and rover. And these 3 components have to be able to communicate wirelessly. The sensor provides X and Y position data to the controller. The controller uses the X, Y position data and converts it into radiuses with an algorithm, and the rover uses the radiuses to drive across the given map.
The sensor unit is what we use to find our XY position for our rover. It does all the positioning, so basically it's the only thing that's responsible for keeping track of where the rover actually is on the field. Going ahead, we're generating XY Cartesian points for it. That way we can send it back to our controller and say we're at the XY position, and it can go ahead and adjust the rover's movements to keep it on track moving from point to point. Because of the way the algorithm works, we need the sensor to be able to generate data as quickly as possible. The reason for that is that the farther the rover gets to move between sensor readings, the more likely it is to get off track. It's running at 200 hertz, and then it's sending messages to the controller with the relevant XY position data at 20 hertz. The sensor controller is divided up into 3 main parts. There's a LiDAR sensor mounted on top, which is what we use to measure the distance between our center origin point and wherever the edge of the rover is. We have that mounted on top of a servo, and the servo allows us to sweep the field between 0 and 90 degrees so that we can keep track of the sensor as it's moving, because of the fact the LiDAR has a very, very narrow field of view. It only has around a 1 degree field of view on either side, so it's pretty much a straight line to the rover. So that servo inside of it has a potentiometer on it, which that will be used to measure the specific angle for when we're doing it. And then whenever we're done calculating the position of the rover, and it finds the start and the edge end of it, we go ahead and we combine that and get the XY position, and then we send that out through the UART. So the sensor is composed of 2 main units. It has the LiDAR, which is mounted here on the top, and it's just mounted onto a bracket, which is then attached to the servo. The servo, it'll go ahead and it'll rotate along, which lets us do all of our readings so that we can keep track of everything that's on the field. Coming out of the bottom here is our main servo controller, so that has the PWM lines and the voltage and ground. It also has a line here, which is attached to a potentiometer inside of it, which is useful because we're able to keep track of the angle as it's adjusting. The way that we're doing ours, we need to continuously track things. So there would have been 2 options to do this. We could have either set it to every single angle and delayed to get to the specific angle and then do our readings. The way we chose to do it is we set the servo at 1 angle, and we go ahead and we tell it to sweep to the far opposite extreme. And as it's moving, it's going to go ahead and do all of its readings within it while it's reading the ADC value to determine the position so it can match those with it. When this is running, it'll start at one end, and it's going to go ahead and it's going to move along until it finds the edge of the rover. Once it finds that one edge of the rover, it's going to continue moving, keeping track of all the data until it hits the other end of the rover. Once it hits that end, it triggers it to tell it to convert the data that is collected into the XY position that we're ultimately going to send out, and it reverses the direction of it. When it reverses, it's just going to start again, and it's going to move until it finds the edge of the rover again, and then it's going to continue moving until it finds the other end, and it just repeats the process. Okay, so I'm just going to go ahead and run through how the sensor system works on a task type basis. So the first thing that's going to happen is we have a timer which is controlling the entire system, and that one is running at 200 hertz. Now when timer 3 goes off, It does a couple things. I'm going to go ahead and trace through getting the distance readings first. So in that case, timer 3 is going to go off, and in that timer is going to set an external pin low, which is going to trigger the LiDAR to start its reading. And when that's set low, the LiDAR starts doing its reading. It's going to take the time it takes for it, and when it's done doing the reading, it goes ahead and it brings an external pin high. Now, we read that external pin through an external interrupt, so when we see the rising edge on it, it's going to go ahead and trigger that interrupt there, which is going to send a message into an I2C queue, which communicates with our I2C thread, which says, okay, I'm ready to do a reading. So that thread is going to go ahead and it's going to send a read to the LiDAR. So it's going to communicate with the ISR, which will then communicate with the LiDAR, and then it'll also take the reading back. At the end of that reading, it's got the distance here, and it's going to send the distance to the sensor thread through the sensor queue. That gives us half of what we need to do our position. The second half is to get the angle. So we go back to the timer interrupt as well. When that timer goes off, it puts a message into our servo queue saying that a time period has gone off and it needs to get a ADC reading. During that, it's going to go ahead and take its ADC reading from that, and it's going to put it back into the sensor queue and send it to the sensor thread. And the sensor thread at this point will go ahead and have all the information it needs to do a reading. So that gives it the XY position if it's found. If it's not found, it's going to continue moving. If it's found the start edge and the end edge, it needs to go ahead and adjust the position of the servo and sweep back the opposite direction. So from the sensor thread, it once again communicates with the servo thread and says, change the direction, and it'll go ahead and it'll swap the extreme that it's at. So if it's sitting at 45 degrees, it'll go ahead and adjust it to go to 90 degrees and sweep the opposite direction it was currently moving. And then back within the sensor thread, whenever it's finished reading and it's ready to send a message, it's going to go ahead and it'll just send it out to the UART structure that was explained earlier. So when we were setting up the sensor system, we had a couple of limitations that we ran into. The first one being is the LiDAR has a resolution of 1 centimeter and it has an accuracy of about 1.5 centimeter. That was some error. We also had error that was coming in through our ADC values. They weren't 100% accurate, especially as the servo was moving. Depending on when you would start the reading, it would be slightly off on one direction or the other, which combined to our error. What's generally happening here is our LiDAR is going to be doing readings as our servo is moving. So the first reading might be down here, and it's not going to see anything, so we just discard that data and continue moving. Now, eventually, it's going to go ahead and it's going to see this point here, which is our first edge, and it's going to say, okay, we've found the rover initially, and it's going to start collecting data points. As it collects data points, it's going to continue to move across the rover, and you'll get more and more data points as you go, all the way until you hit the end edge here. At that point, when it hits the end edge there, it triggers it to do a new calculation, and it's going to go ahead and reverse the direction. That'd be the ideal theory of how it was working. Unfortunately, because of the moving parts and the resolution errors and all the other errors I previously mentioned, our readings that we were getting on the rover looked a lot more like this. So our first reading might look like it's positioned down here along that path. The next one might be spot on. I might do another reading that's up here, another one that's on, and then another one that's back here, and then finally get one that's up here for the final point. That data doesn't really do us a lot of good, because you can't just look at it and say, find the closest point and use that to calculate, because our closest point is up here actually, and that's not where our rover is positioned. So to overcome that error, we took all the points that it found, and we went ahead and we averaged all of them, and then stripped away any of the data points that fell outside of the standard deviations of it. That way, we would go ahead and eliminate some of these bad data points and have data that was much more accurate to look at. And then we would average these together to get our final data point which would give us something like a position in here. Now, it wasn't 100% accurate, and it did slightly vary, but it was consistent enough that we were able to implement in our final system. So to kind of overcome these errors that we were having, another thing that we did was we put a dome around the rover. For one, it made the rover a little bit larger, and two, it was a circular shape, which made it a lot more consistent for when the rover's orientation would change, we would always be looking at the same shape. So no matter where we looked on it, we were always seeing that same arc, which helped make the data more consistent. So when we're looking at that final XY position, it was varying a lot less. A couple things that we would do in the future to try and make it more accurate was the way that we're initially doing it right now is we're setting the rover's angle, and that angle is going ahead and is sweeping from one extreme to the other without stopping in the middle. So once we start it, we are just reading the ADC value to see where it is, but we're not physically adjusting it, and we don't have any control over it. So that moving part, it may play a factor in making the LiDAR a little less accurate as it moves, because it may start a reading, for example, down here, but by the time it finishes the example is up here. So the data point that it's going to generate for it is not always going to be 100% accurate, and there's room for error. And then plus, if you go ahead and add the resolution errors and all the other errors, it gets even farther off. Another thing that we might try to do in the future, it would be to basically, instead of sweeping from one extreme to the other, we would set it to go to a specific angle, wait, do a reading, and then move to a next angle. That way, when we're doing a reading, we make sure that we're always sitting right on that data point, finishing it, and then moving. Starting a reading, finishing it, then moving. That would do two things. It would give us a greater control over where it was reading. We would know exactly what angle it was at, and we can make sure that for those distances that get farther away, we can put more points on the rover that's doing a specific reading.
Discuss the control algorithm. The algorithm was split into two parts, the PID algorithm and a feed-forward approach. We use the PD algorithm and no integral component. The error for the algorithm was the distance away from the line segment. So above the line was a positive distance and below the line was negative distance. And this was multiplied by the KP gain value to give us the first part of the PD algorithm. Now the derivative portion was used to help stabilize the system and make sure the rover is following the line correctly. And typically, the derivative component is not used in most PID algorithms because of its unstability, but in this case we used the derivative component with the orientation of the rover. And the way we handled a little bit of the stabilization issues was to take a history of all the XY data points to make sure that if the orientation did change drastically, it would not affect the algorithm too much because it's an average. So we took a history of the X and Y data points, about 20 points, and we used those values, average them together, and use those for our orientation. And we would subtract the orientation value from the orientation that the map would have. For example, if the specific line segment was at some angle, this would be set back to 0 by subtracting out the orientation of the actual line segment from the orientation of the rover itself to make sure that we were on the correct angle the entire time. And finally, this orientation value was divided by delta t to simulate the orientation change over time. And delta t in this case is the message rate that is being provided by the sensors, because the sensors drive the entire system. And this is eventually multiplied by the KD constant, which completes the PD algorithm. Now, one caveat with the PD algorithm was that we took the inverse of it, and that is what the radius actually was for the rover. And this is because this value will typically be a small value in the decimal ranges. And so if you were given a very, very small u of t, you would have a extremely high radius, and which is what we want because it's very close to the line. So you want to give it a high radius so it doesn't change drastically. And in the case that u of t is large, we'll have a small radius, which will cause the rover to instantly try to change back towards the line. And this is why we used 1 over u of t for this part. Next, I'm going to discuss the feed-forward approach. Alright, so the feed-forward approach is used when we want to change line segments, because the PD algorithm cannot handle an extreme set point change from the distance of the line. So we turn the algorithm off the moment we get to a specific distance from the two line segments. We have a minimum radius set to 5 centimeters set by the rover. And once it reaches this specific distance, the feed-forward approach kicks in until it reaches the minimum 5 radius on the other line segment. And so the way it works is this theta value we can get from the two line segments, and with some geometry we are able to get this entire theta value, which will help us calculate the arc. And this is the equation we generated. And so we have the arc for from the minimum radius and the entire piece right here, and then we use this arc value divided by speed times delta t to give us the number of cycles we want. And in this case, delta t is again our message rate, and so the counter is decremented until it reaches 0, and then the value, and then the PD algorithm kicks back in. And in this case, the value that we send across to the rover is the minimum radius.
And the cracks begin to show.
System. This system only communicates with the control system. The sensor system is going to keep track of the rover system while it's navigating the course. It's going to send that data to the control system. The control system is going to send either a direction it needs to turn at. Those directions will vary from 0 to 3 in integers, which will correspond to 0 being stop. Counterclockwise, and 2 will be clockwise. 3 is just to go straight. And all that communication is going to be done through wireless module, a WAFLA module. That's going to go through a UART sequence, which was already described previously, and it's going to populate a queue. This queue is going to be the queue that I use to basically start everything in the rover system, initialize the motors and speeds and things like that, all my initial variables to a different variables accounting for what I need to turn at, the radius I need to turn at, and direction, or it's going to use that queue to basically trigger when the PI algorithm is going to actually run. To do that, I have a trigger that differentiates between if this is a control command, or if this is basically just me doing the PI algorithm. I populate when I need to do the PI algorithm approximately 20 times a second using a software timer. And that's about the same rate that the control system is sending me commands. So these commands, like I said, just fill this queue, and I just pull from it, one at a time. And depending on which signal it is, which command it is, I do the appropriate thing. And so once the rover thread starts, it basically runs through, like I said, if it's a control command, it does all the initializing of the variables and speeds, what speed each motor needs to be going at. The whole system, I try to get it to around 3.5 centimeters per second, whether it's going straight, whether it's turning at a radius turn. And the PI algorithm adjusts to make all that happen. It reads from the encoders to keep track of where it's at, how fast it's going, things like that. And to do that, I have 2 external timers that are set up. Each one reads from a different motor, so there's 2 motors. And every single time I read from those motors, I clear them. So I'm clearing them about 20 times a second. I'm reading them about 20 times a second. And the reason I do that is because I only want a small sample size of this distance that it's going. Because I use that distance to approximate what radius I'm turning at. And to do that, I use geometry, and the only way that geometry will work is to use small areas or small values of distance. But convert it into that'll be centimeters, and I'll adjust each motor accordingly based on if it's too much or too little, what I need to turn at, what speed I'm going at. After I calculate all that data, I'll then send feedback data to the control system. That feedback data will have what radius I'm actually turning at based on what I calculated from the encoders, and it'll have the speed that the system's actually going at. So I'm now just going to go into a little bit more depth on how the rover system is implemented and works. Basically, I use a master queue. This queue is what I'm going to block on for the whole system. I'm filling this queue myself with the rover system with a trigger like I said previously, that'll trigger the PI algorithm, and also the control system is sending me commands that's going to fill this queue about 20 times a second. And if I get a control system command, I'll do a motor setup. In this setup, I'll figure out which case I'm in. We have a stop and a start case. The stop case will be a direction of 0 and a radius of 0. The start case will be a direction of 3 and a radius of 0. And besides those 2 special cases, I'll either be turning a counterclockwise turn, a clockwise turn, or I'm just going to be going straight. And I'll also figure out my variables in this case, such as the speed of what each motor needs to be set to achieve those radius turns. If it's straight, of course, they're both going to be set to 3.5 centimeters, because that's what my system's going to be running at, or approximately running at, is about 3.5 centimeters, whether it's going straight or it's turning. To do the clockwise turn, I would be going right turn. The rover itself is 10 centimeters wide, so I'll take half of that, the radius of the rover, which is 5 centimeters, and I'll take the radius that he gives me, and for the smaller side, or the side that's going slower, I'll basically subtract 5 from the radius. The side that's going to be going faster, I'll add 5 to the radius, and then I'll calculate the speed that each rover needs to turn at, or go to achieve that turn. And then in the PI algorithm case, I'll calculate the ideal pulses. This is taking the speed, the ideal speed that I calculated in the motor setup for which turn I need to do. I'll take the ideal speed of each motor and I'll convert it into pulses. I'll take that ideal pulses and I'll subtract it from the actual pulses that I have. And based on the differences in the pulses, I'll run that through my PI algorithm, and I'll generate an integral error, which is just the sum of the error pretty much while the system's running, the whole time the system's running. That'll be that error, and then there's going to be a present error, which is going to take that error at that exact moment when I calculate the differences in the pulses. I take those and I run them through the PI algorithm, and I convert them into present error values that'll be used to basically set what each OC of the motor, output comparator of the motor, value needs to be. And so I keep track of what they're presently at, and I'll add to them or subtract from them based on the present error. And that'll change the motor speed accordingly to achieve the actual radius turn and to actually go the speed that the whole system needs to go. This is showing about figure out what radius I'm going at based on my current encoder values, which I send to the control for feedback. This is done, and basically I take the larger side, which I call G, and the least side, which I call L. So if this is the rover is 10 centimeters wide. This track is traveling this amount of distance every 20 seconds. This one side's going to be going at a greater speed than the other, cover a greater distance than the other. I take the greater side, I take the proportion of the greater side, which is going to be this X value that I don't know, plus the diameter of the rover, and then I'll use a proportion based on the least side, and this X value I don't know, to find the radius that I want, which is this X value plus half of the radius of the rover, which is about 5 centimeters, to get the radius that I've traveled at.